Now we're going to start the topic of stoichiometry. It's just a really fancy, cool word that stands for calculations based on a balanced chemical equation. So you can tell all your friends and family that you're doing stoichiometry. It sounds so cool, or maybe not. Anyway, what that is, just that you're going to be doing calculations based on a balanced chemical equation. Remember this equation? We did this in the previous video. We had propane gas plus oxygen will produce carbon dioxide and water. When we balanced it, we put a 3 here, we put a 4 here, 3 times 2 is 6 plus 4 is 10 oxygens, we put a 5 here. So this is our balanced chemical equation. In order to do calculations based on this, we need to start talking about what these numbers mean. There's a microscopic scale and a macroscopic scale. The microscopic scale means that you can say 1 molecule of propane, C3H8, reacts with 5 molecules of oxygen gas to produce 3 molecules of carbon dioxide gas and 4 molecules of water liquid. Okay, so we can write G, 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 and we can write an L here for liquid. So basically, these coefficients would represent molecules. The macroscopic scale, the bigger scale, the one that we're going to use when we're doing calculations, is instead of considering this 1 molecule, we're going to say 1 mole. So we're going to say 1 mole of propane molecules reacts with 5 moles of oxygen molecules to produce 3 moles of carbon dioxide molecules and 4 moles of water molecules, okay? Because we can think of them as molar quantities, we can create something called a molar ratio. A molar ratio is just a relationship between coefficients of 2 different things. For example, you can say, for every 1 mole of propane, you're going to be reacting it with 5 moles of oxygen. This is an example of a molar ratio. You can also say for every 5 moles of oxygen that you're going to react, you're going to need 1 mole of propane. Okay. Another molar ratio. For every 1 mole of propane, you're going to be producing 3 moles of carbon dioxide. So you can mix and match any 2 things in a balanced equation to create these molar ratios. You can also say, for every 4 moles of water that are produced, you're going to be also producing 3 moles of carbon dioxide. Relate these 2. You can relate this with this. You can relate this with this. You can relate this one with this one. You know, mix and match any 2 and flip the molar ratios, you can make a whole bunch of them, okay? Why is this important? Well, if we know a quantity of one substance and we want to know the quantity of another substance, you're going to need the molar ratio to relate the 2. So let's say, for example, on a really simple level, you knew that you are going to be producing 2 moles of carbon dioxide. And you want to know how many moles of water will be produced at the same time. So you know that in this reaction, this hypothetical reaction, you produce 2 moles of carbon dioxide. Well, what you do is you can relate carbon dioxide to water through the molar ratio. For every 3 moles of CO2 produced, you will be producing 4 moles of H2O. Knowing dimensional analysis, and we're going to use dimensional analysis over and over and over again, knowing dimensional analysis, you know that in order to cancel out moles of CO2, you're going to need to put moles of CO2 down here. And to end up with moles of water, you need to put moles of water up here. So now all we have to do is put the coefficients from the balanced equation in the molar ratio. So in front of CO2, you put a 3, and in front of H2O, you put a 4. So how many moles of water are you going to be producing? Well, you just calculate it. 8 divided by 3 is 2.66667. I have this as 2 sig figs, so I'm going to just write 2.7 moles of H2O. So for every 2 moles of carbon dioxide that are going to be produced, you're going to be producing 2.7 moles of water. And you can keep doing this with any of the two. Let's say you had 3 moles of oxygen, and you wanted to know how many moles of carbon dioxide will be produced. So you're going to use up 3 moles of oxygen. You want to know how many moles of carbon dioxide will be produced when you're grilling. Okay? All right, you want to get rid of moles of oxygen. You put moles of oxygen down here. You want to end up with moles of CO2. You put moles of CO2 up here. How do we get the numbers? We get them from the balanced chemical equation. You use the coefficients of the balanced chemical equation to create these molar ratios. So what number is next to the oxygen? 5. What number is next to the CO2? 3. So 3 times 3 is 9, divided by 5. Can't do it in my head. It's 1.8. So we write 1.8 moles of CO2. Let's pretend this is 3.0. Okay, so it's 2 sig figs. Okay, so that's how you use molar ratio. Well, what if instead of them giving us moles, they gave us grams? What if they said you have 10 grams of oxygen? Remember, oxygen is a diatomic molecule. You have 10 grams of oxygen, and the question is, how many grams of carbon dioxide will be produced? So we don't have moles of oxygen, we have grams of oxygen. Now, the only way you can relate oxygen to carbon dioxide is through the molar ratio. For every 5 moles of oxygen, you're producing 3 moles of CO2. Well, I don't have moles of oxygen. Instead, I have grams of oxygen. So we know how to convert grams to moles. How do you convert grams to moles? You need molar mass. All right, so let's see what our strategy is. We're going to go from grams of oxygen to moles of oxygen using molar mass. How do we get molar mass? Go to the periodic table, add up the masses of the 2 oxygens, you'll get the molar mass of 1 mole of O2. Once you have your moles of O2, you can then use your molar ratio to relate it to moles of CO2. So this conversion factor is going to be molar mass. This conversion factor is going to be molar ratio. So this is going to be used anytime you are given grams and you want to get grams of another substance. The strategy is to go from grams to moles using molar mass, and then to go from moles of one substance to moles of the other substance using molar ratio. Where do we get molar ratio from? The coefficients of the balanced equation. Once you've got your moles of CO2, the problem is looking for grams of CO2. So you can go to grams of CO2, and here you're going to need molar mass of CO2. Chemistry is all about logic. There's some memory work here, but honestly, it's the logic of it that makes you retain it so much more. If you're the type of person that just wants to memorize a bunch of facts, it's really going to be hard for you to really understand chemistry properly, because chemistry is logical. You've got to be able to understand why you're doing a step. And when you understand it, you will then everything will be so much easier. And especially those of you moving on into higher level chemistry, understanding the concept of chemistry will take you really far, because memorizing, you tend to forget things if you just memorize them. All right, so anyway, this is our strategy. Now let's actually do the math. I'm going to do it up here, okay? So we've got 10 grams of oxygen. The first step is that we need to convert our grams of oxygen to moles of oxygen. So we need the molar mass of oxygen. You go to your periodic table, you see the mass of oxygen is 16. You have 2 of them, that's 32. So you say 1 mole of O2 is 32.0 grams of O2. Why did you put the 32.0 on the bottom? So that you can cancel grams. That's the whole point, okay? Again, dimensional analysis here to haunt us forever. All right, now that we have our moles of oxygen, I can relate moles of oxygen to moles of CO2. Now I can flip from O2 to CO2. What is the molar ratio? 5 oxygen moles will produce 3 carbon dioxide moles. What goes on the top, what goes on the bottom? Let the units guide you. If O2 is here, you're going to need to cancel it by putting O2 over here. So you're going to write here moles of O2 and up here moles of CO2. This way your moles of O2 will cancel. What number do you put here? You use the coefficient. So you put a 5 here, coefficient 3 here. Perfect setup. Moles of O2 will cancel. Now we have moles of CO2 and the question wants grams of CO2. How do you go from moles to grams? You need molar mass, because remember, molar mass helps you convert between grams and moles and grams. So we're going to look up mass of carbon, mass of the 2 oxygens, add them all up. So carbon is 12, oxygen is 16, the other oxygen is 16. You end up with 44.0. Okay? So what's down here? You want to cancel moles of CO2? You put moles of CO2 over here, and you put grams of CO2 up here. 1 mole of CO2 is 44.0 grams. Perfect setup. Okay? So now we've canceled all our units. We're ending up with grams of CO2. The thing that's left is to do the calculation. Let's get my glasses on so I can see what I'm doing here. Okay, 10 divided by 32 multiplied by 3 divided by 5 multiplied by 44, and you end up with 8.25. I'm going to keep all 3 sig figs since this is 3 sig figs. 8.25 grams of carbon dioxide. So what this is telling you is that every time you use 10 grams of oxygen to burn propane, whatever amount of propane, you are going to always be producing 8.25 grams of carbon dioxide. Okay? Good. That's your first big stoichiometry problem, going from grams to grams. We'll do another one in the next video.